here's some compounds that have carboxylic acid derivatives in them. So there's Lyrica, which I think puts you to sleep. I'm not 100% sure. I feel like I saw a commercial for it years ago. Uh, right? It's basically an amino acid derivative, right? If you look at it, it's an amino acid that has two extra carbons, right? You got an extra carbon here and an extra carbon there, kind of. But it's basically an amino acid, but it has a carboxylic acid, right? You have Plavix, which I think lowers your cholesterol. Again, who needs diet and exercise? When you could have this molecule with a sweet, sweet ester in it, like hot dog, chase it with Plavix. Sounds good. Okay. And then this last one is lysergic acid diethylamide, or LSD. So we're going to go on a little tangent now. So LSD is an ergot alkaloid. So alkaloid is the big box that we throw, like any molecule that has a nitrogen in it is an alkaloid, right? So it's an ergot alkaloid. And this family of alkaloids has a lot of different neurological properties and biological properties. And there's one derivative of LSD, like this changes to like an acid, and this double bond is a cyclopropane, that gets made by this wheat fungus. So, like 200 or 300 years ago, if you stored your wheat and it got damp, it would grow this fungus and make LSD related alkaloids. But instead of like getting you high and like seeing dragons and stuff, they just killed you. So people would, like, if they stored their wheat incorrectly, in the colonial times, people would just die. Like we've got refrigerators now. We've come a long way, right? But just a few structural changes goes from, happy dragons. They're happy dragons. Let's hope happy dragons, or whatever other crazy stuff you see, to um, dead. Now, another tangent. When I was in my postdoc, I've met some interesting people in my life. One guy was into the like electronic music like party scene, and he told me about this phenomenon that would occasionally happen in clubs called puddling, which is they would take a vial of water and you'd be like doing your club thing, whatever, right? And someone would just come and dump a little bit of water in your hand. That water was laced with LSD. LSD absorbs through the skin. So you're like, hey, it's Wednesday night. I got to go to work tomorrow, but I'm going to go to this show. And then someone's just like, boop. And you're like, well, this is taking a turn. I guess now we're going to see what I see for the next 8 hours. Oh, God, this was terrible. I was like, that sounds like an awful thing to do to someone. And he's like, you want to come? I was like, no, I'm good, thanks. I'm good. Good. So we have gone through all of the carboxylic acid derivatives. And so now we're going to talk about additions to carboxylic acid derivatives, or just carbonyls in general. All right, so let's look at a ketone or an aldehyde, right? Neither one of these groups cannot leave, right? You can't break a carbon-carbon bond. You can't break a carbon-nitrogen bond under normal circumstances, right? So when you do an addition to a ketone or an aldehyde, right, we'll just use a generic negatively charged nucleophile. You add, you push electrons up. There's nothing else the molecule can do. It's just waiting for you to add acid so that you can protonate the oxygen. and that's it. We're done. Carboxylic acid derivatives, they all have a leaving group. It's really weird, L. A leaving group attached to the carbonyl carbon. So this allows you to do a little bit more in terms of reactions. So when you add your nucleophile, whatever that might be, right? You push your electrons up onto the oxygen. You get this structure here. So this structure is called a tetrahedral intermediate. Okay. So tetrahedral because the carbon in the middle, right there, is sp3 hybridized, and the shape of an sp3 hybridized carbon is tetrahedral. We really went on a limb for that name, right? And intermediate because it's not going to be around very long. So what happens is when we have this leaving group, instead of waiting for a proton to be added to the O minus, the oxygen goes, I'm just going to remake my carbon-oxygen double bond and knock this leaving group off. Now I've got my nucleophile in the presence of a carboxylic acid derivative and, another compound. If, let's say that this compound here is a ketone and our starting compound is an ester. Ketones are more reactive than esters. So this will just keep reacting with more nucleophile. To make an alcohol. Oh, I was so close to making it all fit and look nice. But instead, it did not look nice. Let's say nucleophile, I swear. NU, NU, NU. There we go. It kind of works. So I'm going to actually draw out an example from lab here in a second. But you add to the carboxylic acid derivative, you make your tetrahedral intermediate, and then it will collapse to remake your carbon-oxygen double bond. Then in a lot of cases, that new compound, that carbon-oxygen double bond, then goes on to react with the nucleophile that's in solution to make an alcohol or do the next step, right? So you've seen this in the Grignard lab, right? So if you look at the Grignard lab, right, you start with an ester, and you have phenyl magnesium bromide, and the product you get has two more aromatic rings than the product started with, right? So you basically have two equivalents of the Grignard reagent. So it adds once, you get your tetrahedral intermediate, right? That tetrahedral intermediate collapses, Electrons come down, push electrons out. And I make a ketone. Ketones are more reactive than esters. So the next Grignard reagent, it has a choice. It can either react with the ester or it can react with the ketone. And since ketones are more reactive, it's going to react with the ketone before it reacts with the ester. So every time an ester reacts, it makes a ketone, and then before the next ester is allowed to react, that ketone has to react. Right? So then that will make our alkoxide with our 3 aromatic rings on it. Okay, so there's an MgBr here and an MgBr here. Okay. And then I can add my acid, yoink, and get my product. So you add, you make your tetrahedral intermediate, that falls apart, and then you're going to add again a lot of times. Seem good? We're going to do more examples of this, don't worry. So we have different carboxylic acid derivatives, and each different carboxylic acid derivative has a different leaving group. So we're going to talk about our general leaving group ability for the different groups can be on a carboxylic acid derivative. So first up, we have acid chlorides, the Cl on the acid chloride. This is our best leaving group. Our next best leaving group is the acetate from an anhydride. Then we have the alkoxide, the OR from an ester. Then we have the OH from a carboxylic acid. And then we have the nitrogen from an amide, with that nitrogen being the worst leaving group. So bad that basically the nitrogen goes, yeah, I'm good. I'm going to do some other chemistry that only amides do because I'm not going to leave. Right? So we've got these acid chloride to carboxylic acid kind of all follow the same trends. They all kind of do similar things. Right? We're not going to start at one end of the list or the other. We're going to start kind of in the middle. We're going to start with carboxylic acids. Since carboxylic acids are where all these other groups originate from, we're going to start with the OG. So we're going to start with the carboxylic acids, see what they do, and then build out the rest of the functional groups from there. All right, so carboxylic acids in general need stronger reagents to react compared to ketones and aldehydes. So things that will easily react with ketones and aldehydes often don't react with carboxylic acids, right? So we always need to pick kind of the most reactive thing to react with carboxylic acids. And the reason is pretty straightforward. So we've got an acid and we add a strong charged nucleophile, right? As the name carboxylic acid kind of clues you into, this is an acid. Strong charged nucleophiles are strong bases, right? So the first thing that happens when you mix a strong base or a charged nucleophile, which is a strong base, with a carboxylic acid is you're going to do the fastest reaction in chemistry. You're going to deprotonate the carboxylic acid. So what ends up happening is your nucleophile never gets to really react with the carbonyl carbon of a carboxylic acid. Instead, your nucleophile ends up reacting with a carboxylate salt. Right? So your nucleophile, step one, it deprotonates your acid. Then you've got to have extra nucleophile, right? A whole other equivalent of nucleophile to then try to add to the carboxylate salt. Right? I am going to say that there's usually going to be some metal making like an actual salt here. So you end up with your nucleophile added, and you have a metal on this oxygen and a metal on that oxygen. Okay. So I know you have blocked out most of Gen Chem through extensive therapy. I understand. But hopefully remember that things that are the same charge repel each other, right? Electrons don't get close to each other because they're both negative. They push apart, right? So your carboxylate salt is negatively charged, right? And then you're taking this other negatively charged thing, your nucleophile, and you're making it react. You're making them react together, right? They both are negatively charged. So you've got to have a nucleophile that really wants to react for it to ignore the fact that it's giving electrons to something that already has too many, right? So Grignard reagents aren't reactive enough to do that reaction. They're just like, yeah, I'm good. I'll go do something else. Like I don't have time for this crap, right? You're already negatively charged. I'm good, right? So to add to carboxylic acids, we often use organolithiums. So you're going to have your carboxylic acid. You're going to have your organolithium. And you're going to have two equivalents of that organolithium. And you're going to turn that carboxylic acid into a ketone. Now, you may be thinking, well, we just said that ketones are more reactive than esters, and they should be more reactive than carboxylic acids. How can I make a ketone when I have a carboxylic acid around? The answer is you don't. The reaction kind of goes and gets stuck, and then once you've removed all the organolithium, then you make the ketone. You never have a situation where you have ketone and organolithium together at the same time. So the way this works, right, is you take your carboxylic acid, and then you take your first equivalent of organolithium, and it deprotonates the carboxylic acid. You make your carboxylate salt plus carboxylate salt. There we go. Plus you have killed off the first equivalent of your organometallic reagent, right? So the first equivalent is just running interference. It just runs in, grabs the hydrogen and runs away, right? It's just sacrificed. The second equivalent is what actually does the reaction. This is like old-timey warfare. Like one person runs up, gets shot, then the next guy gets the enemy. Same thing here. First equivalent gets blown up, takes its hydrogen, and then the second equivalent adds to the carbonyl carbon, pushes electrons up, and adds to the carbonyl. Now, at this point, I have a tetrahedral intermediate. Great. This should try to fall apart or collapse back down to the carbonyl. The problem is both the leaving groups are bad, right? They're both already O minuses, right? Because they've got the lithium, right? You could rewrite that as O minus lithium plus just hanging out by it, right? So they're both already negatively charged. If I push an oxygen that's negatively charged off, I get an O minus 2. Can't do O minus 2, right? There's just too much charge for that little atom to have. So the reaction gets stuck at the tetrahedral intermediate. It can't collapse because it can't push either oxygen off the molecule, and it can't push off the carbon groups. So it's stuck. At this point, this is where you add the H plus. Oops, make it black. So you add your H plus here. Does anyone remember what that functional group is called that I just drew? Please don't hurt me like this. Starts with an H, ends with a drate. H blank drate. It is a hydrate. Thank you, Zoom. Right? So it's a hydrate. So I add the H plus, and it's doing a couple things here. First, it's protonating the O minuses and making them OHs. 2, it's going to get rid of, it's going to kill any organolithium that's hanging around, right? And then 3, we can use it to help the hydrate break down and become a carbonyl again. So we've got our H plus. We protonate our oxygen, becomes water. I can push down, push the water out. I have a protonated carbonyl plus water. I can grab the hydrogen, kick electrons down. Oh, I did the same thing in the earlier class. I lost my R's. There we go. There, my R's are back. And then I get plus H3O plus. So when I add the H plus, turns my tetrahedral intermediate into a hydrate, gets rid of any organolithium. So once I make the ketone, there's no organolithium to react with it, and then helps the hydrate break down into the ketone. So it's pulling a lot of work here, right? It's doing a lot of things. What's nice though is that really the overall reaction is you're just swapping, right? The OH is just becoming whatever R group you're adding, right? So when you look at a reaction, if you're not having to draw out the whole mechanism, the reactions are pretty straightforward, right? I can just say, hey, here's my acid. Here's my two equivalents of organolithium. I'm just going to turn the OH into that carbon. Oops. Then H plus. So you're going to do is figure out how many carbons are on your lithium, and that's how many carbons are replacing your OH. So kind of the actual transformation is pretty simple. Like how you get there has a lot of steps, but what's actually happening is pretty straightforward. So we can turn carboxylic acids into ketones. The other thing we can do with carboxylic acids is we can turn them into primary alcohols. So here we need to use lithium aluminum hydride, then H plus, and you're going to remove the carbonyl and end up with a primary alcohol. The mechanism is similar to turning them into ketones, turning acids into ketones. Right? So I'm going to draw out the structure of lithium aluminum hydride for a second. All right, so lithium aluminum hydride, hey, you have 4 hydrides around the aluminum. Each of those are able to go react. So one equivalent of lithium aluminum hydride is providing 4 equivalents of H minus. Right? So step 1 is the same thing we saw before. Right? The first hydride, it's going to grab a hydrogen and it's going to deprotonate the carboxylic acid, right? And you're going to end up with aluminum hydride, H3. So let me draw it out. Now, one of these hydrogens is going to add to the carbonyl carbon, push electrons up, make that tetrahedral intermediate that we saw before. Now, this is similar to the addition of an organolithium, but a little different, right? It's both O bonded to a metal, right? But I've swapped a lithium for an aluminum. And oxygen aluminum bonds are a little more covalent. The oxygen is less negative when it's bonded to an aluminum than when it's bonded to a lithium. So what ends up happening here is the oxygen with the lithium can push electrons out or can push off the oxygen and we'll end up making an aldehyde plus another lithium containing compound. Now, at this point, I can use this lithium O AlH2, or I can just say, hey, another molecule of lithium aluminum hydride comes in here, right? And it's going to do its job that we've seen it do before, where it's a hydride source and it's going to react with an aldehyde, right? So I'm going to have H minus come up, add to the carbonyl carbon, push electrons over, and you're going to get O minus. Here's your hydrogen that you added. I have that lithium chilling out by it. And then I'm going to add H plus, and that's going to give you your alcohol. Seem good? So it's similar, but the big difference is having that aluminum lets the tetrahedral intermediate collapse, right? So right before, when they were two lithiums, my tetrahedral intermediate was stuck, couldn't fall apart. Now that there's an aluminum there, it's able to fall apart. And the aldehyde is way more reactive than the carboxylate ester or carboxylate salt. So as soon as I make that aldehyde, it's going to react with our aluminum, or lithium aluminum hydride, or whatever aluminum salts we have floating around that have hydrogens on them. Seem good? So I know how the mechanism looks, but I want to kind of get you in the habit of a way of thinking here. So when you do your reductions, I'm going to color code my oxygens here, blue and red. Right? So what happens in kind of all the other carboxylic acid derivatives is that you end up always keeping the blue oxygen. And if you look at the mechanism, right, it looks like we're keeping the red oxygen, and we might be, but depending on where the metals end up, you can keep the blue one. And when we reduce acid chlorides, when we reduce anhydrides, when we reduce esters, they always keep the carbonyl oxygen. So just kind of get used to thinking about the OH, that red oxygen is the one that's going to leave, and the blue oxygen, that's the one that's going to stay. All right? But again, super straightforward. Just take any old acid, add lithium aluminum hydride to it, and you're just going to make alcohol. So, new big deal. Does that all seem good? Okie dokie. So, two equivalents of an organolithium and a carboxylic acid is always just going to make a ketone, right? So just remove the OH effectively and add whatever is bonded to the lithium to that carbonyl carbon. So, right, the carbon that has the lithium ends up being the carbon that ends up bonded to the carbonyl carbon. when we have lithium aluminum hydride, right? That's just going to reduce the carboxylic acid all the way down to a primary alcohol. So effectively, oops, you're just getting rid of the carbon, the C double bond O is basically what the transformation looks like. And then down here, same thing as before. We're just going to get rid of the OH and put a aromatic ring in its place. So that carbon is that carbon right there. Reasonable? All right, so next up is something that we've talked about before, which is the Fischer esterification. Right? And this turns a carboxylic acid into an ester with acid. Right, and we talked about this. We had this in the alcohol reaction section because a Fischer esterification requires a carboxylic acid and alcohol, sulfuric acid, and usually requires heat. I'd say like 95% of the time you have to heat them up to make an ester. Right, and we talked about the fact that this works pretty well for simple acids and alcohols, right? So if you just have not a lot of functional groups going on your molecule, this works pretty well. And hopefully, at this point, the vast majority of you have been exposed to doing this reaction, right? You mix some stuff together, you heat it up for a while, and you get an ester, right? Where the SWOT reaction starts to fall down is when you start having like more complicated molecules, right? You start putting like double bonds in there. You can do other reactions. You put other acid-sensitive functional groups. You have an acetal, God forbid, that's going to fall apart, right? So there's some shortcomings to it. But we never talked about the mechanism. I was like, yeah, that mechanism's kind of complicated. You need to know a lot more stuff. You now know a lot more stuff. So let's go over the mechanism for this and see how this actually works. Right? So let's take a simple carboxylic acid. Make our ester. Oops. All right, so we have kind of the same first step we've seen when we made acetals, and we've done a lot of other stuff, right? When you have an alcohol and an acid, the first thing that's going to happen is the alcohol is going to become protonated. So we can take our methanol here, have it react with sulfuric acid. It's a really bad lone pair. Let me erase too much. All right, you have your lone pair. Okay, grab a hydrogen, kick electrons onto your oxygen. Get your protonated methanol. in your sulfate. So the protonated alcohol is what's going to actually be delivering the proton in the next step. Right, so now we've got our carboxylic acid, and we have our protonated alcohol, and we're going to protonate one of the two oxygens of the carboxylic acid, and the most basic of those two oxygens is the carbonyl oxygen. So the lone pairs on the carbonyl oxygen are going to reach out, grab a hydrogen, to protonated carbonyl. Right? So just like when we had ketones and aldehydes, right? Once you protonate the carbonyl oxygen, the carbonyl carbon becomes easier to add to, right? Now it's more positive. So now your alcohol is able to add to your carbonyl carbon and push electrons up onto your oxygen. Okay. We're gonna have two, but we're gonna call this a tetrahedral intermediate. You'll see what I mean in a second when I say we have two. Now, my goal here is to keep the oxygen that's bonded to the carbon, right? To keep the methanol effectively that I just added to the molecule. So I've got to spit out one of the OHs to go back to having a carbonyl. So what ends up happening here is we're just going to move a proton. We're going to have one of these oxygens grab this hydrogen. Now, I've turned my, forget Yodet, I've turned this oxygen into a good leaving group, right? So now that oxygen can be pushed off using the lone pairs from this oxygen. Come down, push those out. And typically, your alcohol is used in excess. A lot of times your alcohol is, can be close to solvent, or one of the two components is either the carboxylic acid or the alcohol. But there's usually enough excess alcohol around that you can have that alcohol come in, grab this extra proton, give us our ester product, plus regenerate the protonated alcohol. Those are both kind of tetrahedral intermediates, right? Our carbon's sp3 hybridized. It's looking to fall apart to go back to making a carbonyl. So we just move the proton that gets the tetrahedral intermediate that we need. So I often do a bad job of writing this in the problems, but the sulfuric acid is catalytic, We only need a little bit of sulfuric acid to make this reaction go, because every time we make an ester, we regenerate that protonated alcohol, right? So you really only need like a drop of sulfuric acid, because every time the reaction works, you regenerate the thing the sulfuric acid made to go do the next reaction. So, in theory, you could be like, I need exactly 1 molecule of sulfuric acid, and I can do this esterification of an entire mole of carboxylic acid, because I'm always going to keep remaking the reagent I need to go do the next step, to go do the next reaction. It would just take a really long time, because it's like 10.02 times 10 to the 23rd, and you're asking your sulfuric acid to that 1 proton. I need you to do this 10 to the 23rd times, please. It'll take a while, but it would work, because you keep regenerating that. And again, all these steps are in equilibrium, so you can go all the way from acid to ester, and then later on we're going to see that you can go from ester back to acid. So that's why you need either the alcohol or the carboxylic acid to be in excess, because you need to shift the equilibrium towards the product, right? You need to have a whole bunch of starting material, so it pushes everything towards the product. And again, like, this is, you want as many of these problems on your exam as you can get, right? These are just easy money. Also, don't get, hung up on what is your starting material and what is your reagent. As long as the carboxylic acid and the alcohol are in the molecule at the same time, or in the flask at the same time, they are going to react and make an ester, right? So it doesn't matter kind of how they're arranged when you're writing out the equation. It just matters that they're going to be in the same flask at the same time with some sulfuric acid around. You could even, have a situation where you just like have them written all together. Still going to make the ester. So as long as they're all in the same flask, they're all going to react. So something that might have got lost on you in the mechanism that I want to point out real quick as well is you've got your acid, you have your alcohol. You always keep the oxygen from the alcohol. So in the end, when you make your ester, that red oxygen is the one that ends up in the product. The blue oxygen from the carboxylic acid is what gets spat out as water. So you always keep the oxygen from your alcohol. So far, so good? So like I touched on a second ago, and we talked about in the alcohol reactions, right? If you have double bonds in your molecule, your reaction's not going to work well, because, right, you're going to have all these additional reactions that you can do. And we got around that when we talked about alcohols by saying, oh, we can use an acid chloride, right? We could just do an acid chloride reaction where we're like, oh, I can have this double bond, but I'll just have my acid be an acid chloride. And I can get my ester that way. So now we're going to talk about acid chlorides. Right? Again, something that we've talked about previously. But now we're just getting a little more depth. Right? So here's your acid chloride, right? You've got a carbonyl carbon that has a chloride bonded to it, right? So you replace the OH of a carboxylic acid with the CO. Oops. This is the most reactive carboxylic acid derivative. And the reason for this is when you look at an acid chloride, right? The chloride is an electron withdrawing group. It's pulling electrons away from the carbonyl carbon. So the chloride makes the carbonyl carbon more positive, but doesn't use its lone pairs for resonance. So it's just pulling electrons away from the carbonyl carbon and then is doing nothing to stabilize it through resonance. Right? So it's basically, you just got an electron withdrawing group on your carbonyl carbon that's not doing anything to deter the carbonyl carbon from reacting. So it's just like, hey, carbonyl carbon, be really positive so electrophiles can add to you. Right? So where do acid chlorides come from? And again, we've seen this, but not the mechanism. Nope. Apparently, I just draw acid chloride. Let's try again. There you go. So you take a carboxylic acid and thionyl chloride, and you will replace the OH with a CO. So how does this work? Right? You've got your carboxylic acid and then your thionyl chloride. Which looks like this. And you have one of your oxygens from your carboxylic acid attack the thionyl chloride. And just like with the protonating the carboxylic acid from the Fischer acidification, the oxygen that does the reaction here is the carbonyl oxygen. So what ends up happening is, ends up being a lot more arrows, but these electrons here can come down, push these electrons out to add to the sulfur, and I 100% shortcut this and just have you spit out the chlorine. Plus we have Cl minus. Now I've got to make a carbon chlorine bond. I got to get that chlorine to add. So now I can have Cl minus attack the carbonyl carbon, push electrons over. Again, we have basically a tetrahedral intermediate, where now I have to spit one of these possible leaving groups off of the molecule. And this sulfur-containing structure is a really good leaving group. So what ends up happening is you have your lone pairs on your oxygen will kick down and then push the electrons up. And I'm going to do the one-step mechanism here. And it's going to make you're going to make a protonated carbonyl plus generate SO2 and Cl minus. And then this last step, I'm going to cheat, and I'm just going to say, hey, you know what? I'm just going to lose H plus to something in the solution and make my product. Chlorine is like a really bad, chloride, Cl minus is a really bad base. And so you don't want to say, hey, I'm using Cl minus as my base, but there's probably solvent or something else in the molecule that's a little basic that can help pull that proton off. And that will get you to your acid chloride. SO2 smells like rotten eggs. So if your lab stinks, you know the reaction worked. Which there's like a number of reactions. Like we talked about the Swern reaction a while back. That's one that smells like the additive they put in natural gas, that nasty smell that gas has, so you don't blow yourself up, right? Someone would be 2 labs down and run a Swern reaction, and you'd be like, oh man, this is awful. Same kind of thing here. You're like, oh, this smells bad. I guess your reaction worked, but now I smell bad too. Thanks. All right. So we can make acid chlorides. What can we use them for? Right. They're our most reactive carboxylic acid derivative. So let's do some reactions with them. We've already seen that we can use them to make esters. Right. So if you have an acid chloride and you add alcohol, you are going to make an ester. Right. Similarly, if you have an acid chloride and you add a primary amine, you're going to make a secondary amide. If you have a secondary amine, you're going to make a tertiary amide. And if you have a tertiary amine, you're going to get nothing and like it. They don't react.
Oh, you get nothing.
All right. So mechanistically, how do these additions work? They're all the same, right? I'm just changing an atom, but they basically follow the same pattern that we had before, right? Which is on some level, right? You're going to have your acid chloride and your alcohol. Again, we're going to spit out a quick one here and then do the mechanism. I'm going to add to the oxygen, kick electrons up. And what ends up happening is there's a lot of arrows that I'm kind of shortcutting for you guys. Right. I end up with this, which is my tetrahedral intermediate. Oops.
I was asked to share the structures or steps I was cutting out on the way to the tetrahedral intermediate, just to make it make a little bit more sense.
So basically, I'm not allowed to draw this because you don't ever get to have like an O minus and an O plus with like an extra proton on them, right? Because as soon as that starts to form, it's going to become this, where this is going to reach down, grab this proton. So that structure on the bottom there never actually is formed. As soon as the oxygen starts to feel a little negative, it reaches out and grabs the proton off of the oxygen that's becoming positive, because, right, O minus is a strong base. O with three bonds and a hydrogen on it is a strong acid. They're not going to hang out together in the same molecule. So like this, kind of like as this starts to form, it just goes over to this structure where I don't have the charges anymore. Make sense? Because like the general rule is you're not allowed to have like O minus and then like a strong acid in the same molecule. Now this is gonna fall apart, right, to get back to my carbonyl. And right here, the best leaving group on the carbonyl carbon is the chloride, right? So now these electrons on the oxygen here can come down, push out my chlorine. I have one extra proton. And here, might have had a charge on it. I have one extra proton that I got to get rid of. So what ends up happening is you have excess alcohol that can come by, grab a proton. You'll make your ester, and then you end up generating acid as a byproduct in the reaction. And this works exactly the same as if I have amines. I'm just going to replace the oxygen with a nitrogen, but everything is the same. We can also do reductions with acid chlorides. So if you have an acid chloride, you can reduce it with lithium, aluminum, OCCH3, parentheses 3, 3, H. And this will reduce the acid chloride to an aldehyde. And there's a lot of threes going on there. Right? This is a very weak reducing reagent. Only reacts with acid chlorides. So I make the aldehyde in the presence of this reducing reagent, and that reducing reagent is unable to react with the aldehyde, right? It reacts with the acid chloride, but then never can react with the aldehyde. So this will stop at the aldehyde. Any other reducing reagent that we pick is going to reduce the acid chloride all the way to the primary alcohol. So if you had acid chloride and sodium borohydride, that's going to make a primary alcohol. If you have an acid chloride and 2 equivalents of diol, you'll make a primary alcohol. If you have an acid chloride and use lithium aluminum hydride, you'll make a primary alcohol. Now, the 2 equivalents of diol, I want to point this out real quick. We're going to talk about it later. Is diol only has one H minus to give. So great, only has one hydride on a diol. To do a reduction of an acid chloride, I have to go this carbon right here that had the carbonyl carbon on it, right? I have to add 2 hydrogens. I have to add 2 hydrides to it, right? So I have to add 2 hydrides to make to get to that primary alcohol. So I have to add 2 equivalents of diol because each diol only has one H minus to give, right? Where sodium borohydride or lithium aluminum hydride, they can transfer all 4 hydrogens or all 4 hydrides around them to the molecule, so it's no problem. They have extra hydrogens. Diol only has the one hydride, so you need 2 equivalents, 1 equivalent for each hydrogen you need to add. Now, lithium aluminum hydride reducing an acid chloride is kind of like using a bazooka to kill an ant. It's like huge overkill. It's like if you see a spider in your house and you're like, I've got to burn down my house now, right? Like this is where, or even better, if you see a snake in your house, you're like, I got to burn down my house. Actual real story. I'm in a rental in Delaware, vacation capital of nowhere. I'm sorry, student from Delaware, right? And I'm like doing laundry. It's like 9 o'clock at night, and I see what looks like pipe insulation underneath my washer, and I reach down to grab it, and I grab it, and it's a huge black snake, like giant. And like I grab it and it moves and right? Because I'm like, no, right? And then I spend like the next hour flipping over my appliances trying to find this snake, and it's just gone. Like it appeared and then it went away. And I called my mom to tell her about it. She's like, oh yeah, my neighbor, like she kept waking up in the middle of the night and was like, oh, my legs hurt and didn't know why. She had a snake living in her house. It would get up under her bed and like would like bite her in her sleep. I'm like, you can't tell someone that after they've just seen a snake in their house and then expect them to sleep. So like for the next like month before I went to bed, I would like beat my bed with a wiffle ball bat, just like not today, Snake. like leave me alone. No idea where it went. Only saw it once. It went away. Never saw it again for the rest of the time I lived there. Terrifying. All right. So we can reduce them. The other thing that we can do with them is that we can use acid chlorides to make ketones. Oops. And this is a little bit different than how we do it with carboxylic acids. So with acid chlorides, we use a different kind of reagent. Called a cuprate. So this will transfer one of the R groups from the copper to replace the chloride on the acid chloride. So a cuprate looks like this. You've got a copper. It has two R groups on it. It's going to be copper in the +1 oxidation state, so copper 1. So this copper ends up being negatively charged, and it has this lithium that hangs out with it. So you can just take, your acid chloride. I keep using the cyclohexane, but whatever. And then you can have your lithium with, let's say, 2 ethyl groups on the copper, and you can make an ethyl ketone. We start with ethyl because the byproduct, if you start with methyl, is explosive. So methyl copper blows up. No, we're not going to do it. But look, I have a long track record of keeping all of my fingers and all of my students' fingers. Right? So you can do simple reactions with, I usually keep them to things that are easily abbreviated, so they rate all right. Right, so they're easy to rate. So 2 phenols, right? I can add my aromatic ring.
I was asked if the 2 groups on the copper need to be the same. They have to be the same.
Except for in a second. If they're both just carbon chains, they have to be the same. Because the copper isn't able to know which group it's supposed to transfer. So you just can't give it a choice. You have to be like, copper, here are 2 of the exact same things. Give one to the acid chloride, you keep the other. Right? If you put like a propyl and an ethyl, half the time it's going to give the propyl, half the time it's going to give the ethyl. So you just have to be like, here are 2 propyls, give it one. The downside of that is, it's pretty easy when it's like ethyl or phenol or propyl, something you could just easily buy. But what if you spent like 3 weeks making the group you want to put on your copper? You don't want to throw half of that away, right? Because, it can only transfer 1. So what we can do is we can put a dummy ligand. We can put a group that the copper can never transfer onto the copper. And then we only need to use 1 equivalent of what we want to add. So instead of needing to have 2 phenols, you can do it where you have, right, lithium, copper, and then one of the groups is CN. And then you have your phenol. And copper can never transfer, can never give the CN ligand to the acid chloride. So it only ever transfers, in this case, the phenol. So let's say you spent a long time making the group you want to transfer. You would use copper cyanide to make your reagent because it never gives up the cyanide. So you only have to use one equivalent. So, right, you could have a more complicated, right, thing, or, in just this case, propyl, right? And it's just going to transfer. It's actually just a little easier because you're just like, I can ignore, right, the CN. It doesn't do anything in the reaction. It just always holds on to the copper, and then the other group is what you give to replace the chloride. Okay, so just real quick, we'll end on this. So, in the simplest way of looking at this, right, you're like, oh, I need to go from this carboxylic acid to this ester. No big deal, right? But since there's a double bond, you can't just use a Fischer esterification, right? Because Fischer esterification and double bond is no good. So you need to make the acid chloride. So you need to turn your carboxylic acid into an acid chloride using thionyl chloride, right? And then you need to add however the oxygen and however many carbons are attached to it. So here there are 2 carbons on an oxygen. So you get ethanol would be the alcohol that you'd need to add. So I think with that, we could be done for the day.